Okay, so we were talking about what were the conditions that were necessary and sufficient for chirality. And again, keeping this relatively simple, it is that the molecule, the system, is devoid of a mirror plane. If it does not have a mirror plane, void of sigma, then the species is chiral, which means it will exist as one of a pair of enantiomers. It has the property of handedness or chirality. We saw then that that we could designate also stereocenters which have which are tetrahedral sites having 4 different groups around it. But the point is that having tetrahedral centers or having stereocenters does not necessarily make you chiral. Now, there are times when if you have a stereocenter, you are chiral. But I'll show you some examples of where species having stereocenters are not necessarily chiral. So I'm gonna, if I look at, I'm gonna build a molecule. So I'm going to build this species. Actually, this will work. That one. So if I look at this compound, and essentially what this is a compound having 2 stereocenters, right? So this carbon is attached to, white, red, blank, and then another carbon, and it's tetrahedral, so it's a stereocenter. So I've got 2 stereocenters in this compound. In other words, this might be something like butan 2,3-diol, which has 2 stereocenters, or something of that nature, right? It could be, anything like that. The dichloro species. So this has 2 stereocenters. But if you notice, the 2 stereocenters are symmetrically substituted. They've got the same groups of them. So H-methyl-OH, H-methyl-OH, or in this case, H-methyl-Cl. So I've got 2 stereocenters in each of those compounds that are symmetrically substituted. And so these models are proxies for that. So here's the one, 2,3-butanediol. Here's the mirror image. If I look at it this way, they're not superposable. But if I turn the molecule around, which I'm allowed to do, then the molecules are superposable. And if that's the case, then they pass the sameness test, and these are not enantiomers of each other, right? They're not even isomers of each other. So here's a case where I have molecules that possess a stereocenter, or in this case possess stereocenters, but they're not chiral. Because what is chirality? The property that my mirror image and I are not superposable. So everybody has a mirror image. That doesn't tell me anything. They've got mirror images. But the mirror images and the objects are superposable. So this compound is not chiral. It is achiral. So having stereocenters doesn't make you chiral. It's not a sufficient condition for chirality. Now, everything with one stereocenter is chiral. But if I have multiple stereocenters, I can potentially be achiral. And if you notice, if you look at the molecule, part of the reason in my head why I might understand why this species, as I'm holding it, is achiral, is that it has a mirror plane straight down the middle. Okay? And certainly in this conformer, the molecule has a mirror plane and therefore it is achiral. But I will caution you that this is one of billions of conformers of this compound. I can have a conformer like this, I can have a conformer like that, and any number of ones in between. Not all of them, in fact none of them except for this one, has the mirror plane. Okay? So compounds like these are special. We call these compounds meso compounds. And if I were to draw it, I might draw it, for example, like this. I might say I have OH, OH, H methyl, H methyl. And that particular species, as you can tell, has a mirror plane straight down the middle. And so I would call this particular compound a meso compound. So a meso compound is one that has stereocenters, but is nonetheless achiral. Okay, I'm going to come back to this in a second. And you notice I mentioned that the stereocenters in a meso compound are symmetrically substituted, right? OH, H, and methyl. But there's another feature about stereocenters we need to discuss. And one of the easiest ways, I think, of sort of segueing into that discussion is to look at what happened when we discovered the different butenes. So for example, if I put a double bond and I make butene, I call a compound 1-butene. But I can also put a double bond here and make 2-butene. And 2-butene is distinct from 1-butene. The 2 is enough to distinguish this compound from that compound. The problem is, there's another 2-butene, which is entirely a different compound. It's got a different melting point, a different boiling point, blah, 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 blah. So how do I distinguish this 2-butene from that 2-butene? Because 2-butene alone tells me about the constitution of the molecule. Who is connected to whom, and where the double bond is. But what happened here is that a stereochemistry issue arose, because my three-dimensional arrangement of groups differs. So beyond 2-butene, I put in a label to indicate stereochemistry. So I call this trans 2-butene, and I call this one cis 2-butene. And the label cis and trans were introduced to account for stereochemistry. The 2-butene took care of the constitution, the connectivity. The trans and the cis labels take care of the stereochemistry. You remember in the previous part of the lecture, we looked at a CXYZA. We looked at a species, we have just erased it. We looked at a species where I had a stereocenter that had X, Y, Z, and A. And let's pick an example of them. So let's say I'm dealing with this compound. So I have here an OH and let's say an F. So let's say I'm dealing with 2-butanol. 2-butanol has a stereocenter, which is here. It's got the H, which is understood. It's got the OH, a methyl, and the ethyl. So that's the stereocenter. Tetrahedral, 4 different groups around it. But if it's a stereocenter, then there would be a version of this species in which the OH group, if I were to put in now the actual stereochemistry, in which the OH group is in front of the board, and there'll be one where the OH group is behind the board. Okay? That is the essence of it, right? So if I take a species and if it's got a stereocenter, so these are mirror images, then as I'm holding this with the blank up and the red coming towards you, in one of them, the blue is on your right, and the white is on the blue is on your right, and the white is on your left. It's the opposite here. Okay? So as I fix two groups, in this case the methyl and the ethyl, so these are fixed in the plane of the board. In one, the OH is in front of the board, in the other, the OH is behind. Okay? So if I hold the molecule this way, so I fix the red, I'll hold it this way. So if I hold it this way, if I hold it this way, so I have the blank on the right, the red on the left, in the plane of the page, plane of the board. In one case, the white is coming at you and the blue is behind. In the other, the blue is coming at you and the white is behind. Even though I fixed the red and the blank. So the relative positions of the blue and the white are different, right? So if I fix the positions of the methyl and the ethyl, the relative positions of the OH and the H are opposite. One is coming out the board, one is going behind. And listen, a tetrahedron has three groups in the same plane. XCA, and then the other two are out of the plane, front and back. Okay? In this case, methyl, carbon, and ethyl are in the plane of the board, and the OH and the H are coming out and in front and behind. Well, the problem is, if I had to name this compound, what is it? Well, it's an alcohol, so it's all. The carbon chain is saturated, so it's an anol. It's got 4 carbons in the longest chain, so it's a butanol. It's got a hydroxy group with carbon number 2, so it's 2-butanol. That takes care of the constitutional part. The same way the 2-butene took care of the constitutional part. But I know full well this compound is not that compound. So I invent a label to distinguish the stereochemistry. I've got the same problem here. Both of these are 2-butanols. They're not the same. Right? They haven't passed the sameness test. They're different compounds. So I need to invent a label to distinguish this 2-butanol from that 2-butanol. So what we use is the R and S system, right? We use the R and S system, or the RS system, which really, you kind of met the basis of this a little bit. And what we end up using is designations from the Kahn, Ingold, Prelong system. So here's what we do. We're going to imagine that we hold the molecule with the group of lowest priority pointing away from us. And how do we designate priority? Based upon the Kahn, Ingold, Prelong system. This is where we look at the atomic numbers of the atom first attached, the atom attached to the stereocenter. So for example, in this case, O has a higher atomic number than carbon, carbon, or H. So O is priority 1. Okay? We did this when we were trying to figure out E and C configurations, right? If you remember. Carbon has the same priority as carbon. So I'm going to look one atom past. So this carbon is CH2H. This one is CH2C. Since C beats H, this is priority 2. Carbon beats H, so this is priority 3, this is priority 4. So I'm looking at this molecule with a group of lowest priority pointing away from me. And then I'm going to say, if I go from first to second to third, with the group of lowest priority pointing away from me, and I go from 1 to 2 to 3 in a clockwise direction, I'm going to call that species the R enantiomer. If I go from 1 to 2 to 3 in an anti-clockwise direction, I'll call that species the S enantiomer. So I use the Kahn-Ingold-Prelog system to designate priorities. I use the sequencing of the direction of those priorities, 1 to 2 to 3, to determine the configuration, R or S. So how does that work? With 4 pointing away from me, dotted line, as I go from 1 to 2 to 3, I'm going this way. And that is clockwise. That is clockwise. So this compound, I'm going to call it R2-butanol. That's R2-butanol. This one is literally the mirror image. Okay? If I take that compound and I pull it out of the board and lift it here, so there's an invisible mirror at that position, the OH here, which is close to the mirror, will reflect into the OH close to the mirror. The H here, which is away from the mirror, will reflect into that H away from the mirror. And then the methyl and the ethyl reflect each other in the plane. So these are mirror images. What would I call this one? Well, so you know by now that if it's not the R, it's the S. But let's work it out. As I've drawn this, the H is not where it should be. For me to read this, the convention is the group of lowest priority must be pointing away from the reader. Well, in this case, it's not. So I have 3 options. 1, I can say to myself, look, this H is in front of the board. So what I'm going to do is take my vantage point and move myself behind the board. So when I move myself behind the board, I'll be looking out at the H, and the H will be looking away from me. So in other words, I'm going to go from looking at the molecule this way to looking at the molecule this way. So I want you to watch this. So imagine now you are looking at me, and I am taking my finger. So we're looking at the molecule. We're looking at the molecule here. Let's imagine we're going clockwise. Just say we're going clockwise. If I go clockwise, so you're looking down a system, and you're going from 1, 2, 3, and it's going clockwise, right? Now, we're going to change our vantage point by going behind the board. But I'm going to keep my finger, from my perspective, going clockwise. So I'm going to turn, and now looking at it from behind, what you see is that it looks S. It looks anti-clockwise. Now my hand hasn't changed what it was doing. So the point is, when you move yourself from looking from the front of the molecule to looking from the back, it apparently inverts the direction. Okay? So if I move my head into the back of the board and I look out, I will still see R. From my perspective, I will still go in clockwise. From your perspective, looking the wrong way, you see anti-clockwise. In other words, if you look at the molecule, so the group of lowest priority is pointing towards you, read the answer and invert it. So this would have been first, second, and third. So what you would say is this is 1, 2, 3. It looks as if I'm going clockwise, but because my vantage point is exactly opposite to what it should be, I'm looking from the front rather than from the back, this is actually going to be the S compound. So when the group of lowest priority is behind the board, by convention, that's where it should be, read it, take it. When the group of lowest priority is in front of the board, read it and invert it, because you are inverted. Right? You should be looking at the molecule this way. You're not, it's exactly the opposite direction. And so your perspective is inverted. What looks clockwise this way, from this perspective, looks anti-clockwise from this perspective. So in the group of lowest priorities in front of the board, read and invert. Well, sometimes it's not in front and it's not in the back, it's at the side. In other words, what if I took the molecule and I drew this? What if I had this? What do I do then? So the best case scenario is the group of lowest priority is behind the board. The second best scenario is the group of lowest priority is in front of the board. When it's behind, read and take. When it's in front, read and invert. What if it's on the side? Well, I can do a couple things. One, I can move mean. So instead of looking at it this way, which is not going to help me at all, I can put my eye here. So my eye, which looks like a diseased eye, my eye is looking down the molecule so that the group of lowest priority points away from me. In other words, I'm going to put my head here. And if I do that, so the H is pointing away from me, I have OH on the right, methyl here on my left, and ethyl here. In which case, going from priority 1, OH, to priority 2, ethyl, to priority 3, methyl, I'm going this way, and that is clockwise. So this compound is the R compound. Right? So option 1 is to move myself so that I'm in the frame where I'm looking down the group of lowest priority. And if I do that, I can read the answer and take it. That's option 1. Okay. Let's do option 2. Okay, so if I take the molecule, if I take a molecule and I'm going to rotate the group. I'm going to rotate it through to 120 degree iterations. Now watch the sequence. I'm going red, American. I'm going to go red, white, blue. That's how I have it now. I'm going to turn it 120 degrees. So the red, so this is 120 degrees. The red goes here, the white goes there, the blue goes here. Now remember, as I'm turning it, I'm going in this direction where it reads red, white, blue. I'm going to turn it. And if I read it again from here, it's red, white, blue. Another 120 degrees. If I read it starting from the red, going as I'm seeing it clockwise, it's still red, white, blue. In other words, I can turn it so the groups change positions, but the sequence of groups doesn't change. If I start at red, regardless of where I had this thing, it's going to be red, white, blue. If I go clockwise, red, white, blue. If I go clockwise, red, white, blue. I'm going to bear that in mind. So I can then say to myself, look, I'm going to rotate the groups on this carbon. I can rotate it. So remember, originally this is R. I'm going to draw this arrangement, which will be true for all. And then this arrangement. But what would happen if I rotate this going into the board? Rotate into the board. So the methyl will replace the OH. The OH would swing to the H. The H would swing to the methyl. We're just playing musical chairs and we're swapping positions in the sequence. Methyl to OH to H. So the methyl goes here, the H goes here, the OH goes there. One more time, the H will go behind the board, the OH will be here, and the methyl will be here. So now the H is where I want it, behind the board. So I'm going to read it. First, second, third, that is the R. Come on. Or actually I could have said, look, here the H is in front of the board. So I'm going to read it and invert the answer. So this will be first, second, third. It looks as if I'm going S, anti-clockwise. But since the H is in front, I have to invert the answer. So that's R. So option 1 was to move the observer to look down the group of lowest priority. So move me. Rotate me. Option 2 is rotate the molecule. So the lowest priority is no longer in the plane of the page, but it's either in front, but you have to remember to invert the answer, or it's behind, in which case you read it and take it. Rotate you, rotate the molecule. Two different options. There's a third option, which many people find easier, but you're free to use whichever you prefer. And it is as follows. Okay, so these are enantiomers. Okay? Enantiomers. Let's interchange a pair of groups. Doesn't matter which pair. I'm going to interchange the blue and the black, the red, the white and the black. Doesn't matter. I'm going to interchange the white and the black. If I interchange the white and the blank, these are no longer enantiomers. In fact, they're equivalent species. They've now passed the test of sameness. In other words, if I make one or an odd number of interchanges, what I do is I invert the configuration of the carbon. And these are configurations, right? These are permanent three-dimensional arrangements. I invert the configuration. Now, I'm going to do it again. Let's interchange another pair. I'm going to interchange the red and the blank. If I interchange the red and the blank, what I find now is that these are enantiomers. They're mirror images, and they're not superposable. So if I do an odd number of interchanges, I invert the configuration. If I do an even number of interconversions, I maintain the same configuration. The molecule would have appeared to be rotating, but I would have maintained the configuration. So I'm going to take advantage of that. I'm going to say, look, here is my 2-butanol with the H in the wrong position. The H should be ideally behind the page. So I'm going to say, look, here's what I'm going to do. I'm going to draw my species, and I'm going to do one interchange, H for OH. So the H is going to be behind the board where I want it. I'm going to put the OH here. But that's one interchange. Right. That's one interchange. That's not what I need to do, because if I do that, my group is, let me back up. So I can do two things. I can say, look, I've done one interchange, which means my configuration here is the opposite of what it should be, because one interchange flips it. So I can leave it like this and say going from 1 to 2 to 3, this is going anti-clockwise, so this looks like it's S. So if this is the S, and I've done one interchange, well then for heaven's sake, this must be the R. Right? Alternatively, I could push it and do a second interchange and say, move the ethyl. So I'll keep the OH, I'll keep the H behind the board. I'm now going to have the OH here. I'm going to put the ethyl here. I'll put the methyl here. So now I'll go, ET is just ethyl, right? So I'll go 1 to 2 to 3. If I do that, that is R, which is my compound. So I can do one interchange, read it, and invert it, because I've only done, well, read it, but remember, one interchange inverts the configuration. So I'll have to re-invert it. Or just do 2 interchanges, which is, it depends how much work you want to do. And once you've done 2 interchanges, then this configuration and that configuration are the same. I want to make a point here. Configuration and conformation are very different. Configuration and conformation are very different. Conformations are temporary, three-dimensional arrangements. Conformations are temporary, three-dimensional arrangements. So in this conformer, the whites and the whites are eclipsed. In this conformer, the whites are anti. This conformer, the whites are gauche. Okay? But the configuration of the carbons doesn't change by rotation, right? And I know that. This was R. And in this conformation, this H and that methyl have a dihedral angle of 180 degrees. I rotate, but that is still R. Even though it's a different conformation than this one, and I know that because now the OH and the methyl are anti. But the configuration of that carbon doesn't change. So and I rotate again, and now the methyl and the methyl are anti. So I can change the conformation of the molecule without changing the configuration of the carbon. Configurations are permanent. Whether those configurations are trans versus cis, which are permanent three-dimensional arrangements, or R versus S. So configurations are permanent three-dimensional arrangements about a center, about a carbon. Conformations are, well, really about a center. Conformations are temporary three-dimensional arrangements, and they're interconvertible. You can't interconvert R and S, no more than you can interconvert cis.